section 8.1, polar coordinates. So we're going to introduce the polar coordinate system. So most people on planet Earth kind of use polar coordinate system. Let me explain what it is and explain probably why you use it. So let's go right here. So the polar coordinate system uses the distance to specify a point on a plane, distance and direction. So you're going to have your radius here and then your angle. So given points, you're going to start from the origin, or sometimes we'll call this the pole. And each point is given by r theta. And so here, let me kind of explain how this works real quick, and then I'll explain probably why you do this. So here, let's just do this one super fast. So here, I have r is equal to 1, and theta is equal to 3 pi over 4. Alright, so here I'm going to go out my distance. And so this is what the polar graph kind of looks like. So it's a radius 1, 2, 3, and 4. Your degrees, so 0, pi over 4, pi over 2, and just around. And so this is how you graph things. And so here we're going to be on one radius, and then our direction is pi over 4. And so here we are, right here. Okay. So let me zoom on in. And so here, this is what it means for a point. So this is r theta. Okay. Now, why do I think most people kind of use this? So let me explain why most people probably use. Well, let's finish this, and I'll go explain it after that. Okay, so here, and I also want you to find another representation of these points. So, so you can have a unique polar system where you strictly define your r to be positive, and then your theta between 0 and 2 pi. That way everyone has a unique thing. Your book doesn't use that. Your book uses the more free-form one where r can be positive or negative, and pi, your theta can be anything. And so there's not a unique representation. And let me kind of show you that. So here, if we had r to be negative 1, and we had our angle to be 7 pi over 4, here we go. So here we go to this angle, 7 pi over 4. And instead of going in the positive one direction, we're going to go in negative one direction. And that will end us back at this point. Okay? So these 2 points are the same. Let's do this again for B. So B, here I have negative pi over 6, which is somewhere along here. These are even marks, and so it doesn't quite, pi over 6 isn't quite on it, so just do it right about here. And we're going to go 3 steps out, so here. So if I drew that out, and so here is my theta. So my theta here is negative pi over 6, and then here my radius here is 3. Right? We can also achieve this, say if we went from 11 pi over 6 and 3. We can also, so instead of going this way, this triangle, we're going to go all the way around this way, theta, and so that's 11 pi over 6, and our angle 3, and so once again we can achieve this. And so your book uses the non-unique format, which is fine. Alright, so let's clean this up a little bit. Alright, let's go ahead and leave the points, but I'm going to clean it up. Let me label the points too. So here we'll have 1, 3 pi over 4. Here we're going to have 3, 11 pi over 6. Alright, let's do this. So we'll have 3 and 3 pi, so we'll be on the third ring out. So R will tell you what ring we're on. So here's 1, 2, and then 3. So this 3 says we're in the third ring out, and our direction is 3 pi. So this is pi, this is 2 pi, and this will be 3 pi. And so we're on the third ring out right here. And so this is 3 pi. Okay, but a more probably succinct way of writing this would be 3 and just pi, right? And notice that gets us to the same point. And our last point here, we're going to have negative, we're going to go to pi over 4, so we're going along this line right here, and then we're going to go in the negative direction, 1, 2, 3, 4, and so this is right here. So this would be minus 4 pi over 4, okay? And another representation of that, of course, would be 4, and then 5 pi over 4. Right, so here we have representations. Here we have some positive and some negative. Technically, just to fulfill the requirement of what I asked us to do. So we want 2 positive and 2 negative. So here I could do -3 and 0. And so here's another one. So if I went here at 0 and went -3, I also can end up again at this point. So there's multiple ways of representing the same point, at least the way your book done it. There's a way of doing it where you strictly say r is greater than 0, and then theta is between 0 and 2 pi, not including 2 pi. And if you make these requirements, your polar coordinates are then unique, as in there's only one way to represent it. Your book uses the more free form. There's reasons to use both. Okay, so let me do something real quick. So let me just go ahead and hide all these notes, and let me add something. So why do I think most people actually use a polar coordinate system? So let's pretend you have your house right here. This is your house. I'll make that a little bit bigger. So this is your home. This is your happy home. And then here, according to you, some over here is your work. Over here is school. And over here is your friend. And what you think of, and so most of the way most people at least run this way, is you know which direction you need to go, and you know how many minutes it'll take. So that, you know, work might be 20 minutes away, and that's distance in terms. So minutes is actually distance it takes in a car. So it's distance in a car, really. So 20 minutes as your car drives, and school might be 15 minutes away. Your friend might live across town and just 45 minutes away. And so most of us kind of use a polar coordinate system when we're just driving around town, in the sense that my house is the center, or wherever you're living at's the center, and then you think of how long it takes and which direction you need to go, right? Which is a distance, and a distance in terms of time, right? And then a direction. And so actually a lot of us use this polar coordinate system in our heads, right? So it's not actually as strange as it seems. When I was sitting there plotting points, yeah, it's kind of weird, right? But when you're doing this, it makes sense. It's like, oh, which direction do I have for how long? And so actually a polar coordinate system is actually really quite useful in many applications. And it's kind of the one you use in your head. You don't really use a rectangular coordinate system. You use more of this coordinate system for at least location and driving. Okay. All right, so let's go to the next page. So that's the relationship between polar and rectangular. So here, x is equal to r cosine theta. So here, notice that this is my r and this is my theta. X is r cosine theta, right? So that would give me this length right here. We've kind of done this before, and y would be r sine theta, right? And to change from rectangular to polar, we'll take r. If we have squared r, we'll do this. We'll just take this equal to x squared plus y squared. And then here, theta is this. Here you have to be very careful to land in the correct quadrant. So make sure you're in the right quadrant. Okay. Okay, make sure you're in the right quadrant. That's important. When you're going from polar to rectangular, rectangular to polar. We'll go ahead and do that, and we'll make sure, and I'll kind of show you what to do. So we'll find the rectangular coordinate systems for this. So 4, radius of 4, and an angle of pi, 2 pi squared root 3. Well, if we want to find the rectangular coordinate system, we're just going to use these formulas up here. So here we have r cosine theta, and r cosine theta here would be 4, that's my r, cosine of 2 pi over 3. And if I crunch this through a calculator, I'm going to get -2. Okay, do the same thing for the y coordinate. Let's go ahead and zoom on in. So we'd have r sine theta. That's equal to 4 sine of 2 pi over 3. and that's equal to 2 square root 3. Okay. So our final answer here, there it goes, -2, 2 square root 3. And so this is in polar coordinates, this is in rectangular coordinates. Okay, to do the opposite, I'll show you how that. So r squared, so this is in rectangular coordinates, is equal to x squared plus y squared. So that means what we're going to have here is, let's go ahead and do this, is r is equal to the square root of x squared plus y squared. So that's the square root of 2 squared plus -2 squared, which is 4 and 4, so this is square root of 8, which is, of course, 2 square root, oops, 2, as my computer catches up. Alright, so here we're going to put the tangent of theta is equal to y over x, so that is -2 over 2. So here we have it as y over x, so -2 over 2. So this implies we just take the arctangent. So remember, arctangent is going to give us values from -pi over 2 to pi over 2. Okay? So we want to make sure we're in the y product. So if we take the arctangent of -1, that's going to give us -pi over 4. -pi over 4 is in quadrant 4. And is that what we want? Well, let's look real quick. If I go ahead and graph this, I'm going to be 2 in the x direction, -2 in the y direction. And so which quadrant am I in? I'm in, this is 1, 2, 3, 4. So I'm in the right quadrant. And so this actually gives me answers, so I don't have to translate it. If it gave you something in the wrong quadrant, just go ahead and move the angle to achieve the right one. Okay? And usually do that by adding a minus and a pi. Okay? So here, our new coordinate system, so this in rectangular is 2, -2. In polar coordinates, it'd be 2, -pi over 4. And since your book uses the more free form, it actually makes it easy. I don't have to retranslate this. If you were using the strict form, you would rewrite this as square root 2 over 2, and then you have to translate that into something between 0 and 2 pi. Well, that's, of course, 7 pi over 4. Alright, so one of the things your book's going to ask you to do in this time is to write things as in polar coordinates. Well, going from rectangular to polar isn't that bad. Going the other way is a little bit of a trick, and we'll do that on the next page, but let's go ahead and do that. So here, everywhere we see an x, we're just going to plug in r cosine theta squared, and everywhere we see a y, we're just going to put r sine theta, because here, remember that x is equal to r cosine theta, y is equal to r sine theta, so you just plug that in and just crunch it through. So here you have r cosine theta equals 4r, cosine squared theta, make sure you do it to each thing, r sine theta, and here I can cancel out an r, so I have r, and I'll go ahead and divide out the cosine. So r is equal to sine theta over cosine theta, cosine squared theta. All right. So this, you can leave it like this. Your book takes it one step. Oops, I forgot my 4. Your book takes it one step forward, and so sine over cosine is tangent, and 1 over cosine is secant. And so your book takes it one more step. I don't know if this is any cleaner than this. I really don't. But it's fine. And so going from rectangular to polar is not too bad. You just plug it in, and then usually you'll solve for r. Now, the other way tends to be a teeny bit more tricky. And so let's go ahead and do that. So here, I have a graph here just for fun. We won't use it too much, but I do want to show you what stuff. So here we have r is equal to 5 secant theta. And we want to write this in rectangular coordinates, right? And if possible, determine the graph. So two of the graphs we can kind of do. One of the graphs is just a little bit out of our range, so we won't worry about it. The graphing these is actually next section, so we'll tackle that in the next video. But here, let's just switch this from polar coordinates to rectangular. And so what we're going to be using here is that r squared is equal to x squared plus y squared. And then we're also going to be using that r cosine theta is equal to x, and then r sine theta is equal to y. You usually don't use the tangent, but you can. But we're usually going to be mainly using these things to convert r's and cosines and sines into x's and y's. Okay. So here, let's go ahead and do that. So here I have r, and I'm going to move this secant over. So it's r equal to 5 over cosine theta. Let's write it that way. Then this is r cosine theta equals to 5. Once we have something that looks like this, we can just swap it out for an x. Okay. So one of the things that you try to do is to get r cosine thetas or r sine thetas. Once you have an r cosine theta or r sine theta, write it as either an x or a y. So here, I notice here I could probably get an r cosine theta pretty easy, right? So I just wrote secant as 1 over cosine and then moved it over and then here. And then we actually could graph this. So we'd be out 1, 2, 3, 4, 5, somewhere out here, and we just have a nice little line, right, of x equal to 5. Notice that this line here is the same thing as graphing r equals to 5 secant theta. And then we get this line. Now how we get this line from that, that's for the next one. Okay? So here, can anyone guess what we're going to probably do? We're probably going to try to get r sine theta somehow. So in order to do this, we can move it over, then we'll have like a cosecant. That's not too useful. And so one of the fun tricks, one of the tricks that appear often, is that you're going to multiply by r. And so here, we're going to multiply by r squared. So if we just see a single r, often we multiply by another r to get r squared, because that will achieve this. And then it actually makes it easier here, since this will achieve this. So here, 2r sine theta, and so this means x squared plus y squared equals to 2r sine theta is y. Okay, and just for the sake of fun of learning how to graph this, we'll go ahead and finish this. So here, I can move over that to y and set this equal to 0. Then I can complete the square. And I complete the square by adding a 1 here and a 1 here, and so this becomes y minus 1 squared. Because if I add a 1 here and add a 1 here, this becomes y minus 1 squared, and this is equal to 1. What is this? This is a circle centered at 0, 1, and with a radius of 1. So it's a circle like this. And so that's what this one is. Okay. We will actually graph this using polar coordinates to show that this ends up producing the same thing. Right? Now something really complicated like this. Unfortunately, there's not a real clean and easy method to do. So here we have a single r. So what you usually do with single r's is you just multiply everything by r to get an r squared. So here I get r squared equals 2r plus 2r cosine theta. Alright, so r squared is equal to x squared plus y squared. So remember, usually when you see a single r here and here, you multiply by r. Now, can I multiply it by r here? Sure. But then I would have the secant to deal with, and it would have been kind of weird. This one, it makes sense to do here. But over here, you'll get this in trial and error. It takes just a lot of practice to get these. There's no surefire way to always do this, which makes it kind of hard for students. I understand that. So let me show you a couple, and then you'll work on a couple. All right, so here we have 2r. R cosine is just 2x. Okay, so I'm going to move the x over. So I'll have x squared minus 2x, oops, make that look like an x, plus y squared equals to 2r. Here I have a single r, so I want to just, in this case, instead of multiplying everything by r, I'm just going to square both sides. Because if I square both sides, I'll get my r squared as desired. Remember, try to build r squares to get rid of single r's. or attach them to this. And so here we have no more sines or any more trig functions, so it's best just to square. So here I get that, and so I'll get x squared plus, minus 2x plus y squared equals 4r squared. Well, 4r squared is equal to 4x squared plus y squared. And so that's our final answer. Now this is kind of a beastie thing that, we don't really know how to graph, right? This isn't apparent on how to graph this. So we'll show you how to graph this instead using polar coordinates in the next video. All right, and that's the end of this one.